Welcome back to the video on Chapter 21, Tests and Intervals, or more on tests and intervals. Alright, so more on alpha levels. The p-values given the reader, so again, when you have a situation that you're answering or finding the answer to, the p-value gives you far more information than just stating that you reject or fail to reject the null. In fact, by providing a p-value to the reader, you allow that person to make his or her own decisions about the test. What you should consider to be statistically significant might not be the same as what someone else considers statistically significant. There is more than one alpha level that can be used, but each test will give only one p-value. So, there's something that we need to talk about with significant versus important. So again, what do we mean when we say that a test is statistically significant? All we mean is that the test statistic had a p-value lower than our alpha level. Again, then we would reject our null hypothesis. But please don't be lulled into thinking that statistical significance carries with it any sense of practical importance or impact. So, for large samples, even small, unimportant, insignificant deviations from the null hypothesis can be statistically significant. Again, when you have a large amount of samples, lots and lots of data. On the other hand, if the sample is not large enough, even large financially or uh, scientifically significant differences may not be statistically significant. It's good practice to report the magnitude of the difference between the observed statistic value and the null hypothesis value in the data units, along with the p-value on which we base our statistical significance. So again, most of this is what we did in Chapter 20. The confidence intervals and hypotheses tests. So the confidence interval and hypothesis tests are built from the same calculations. They have the same assumptions and conditions. You can approximate a hypothesis test by examining a confidence interval. Just ask whether the null hypothesis value is consistent with a confidence interval for the parameter at the corresponding confidence level. So again, see how this all ties together with Chapter 20? Because the confidence intervals are two-sided, some of them, in this case, the not equals is two-sided, they correspond to two-sided tests. In general, a confidence interval with a confidence level of C% corresponds to a two-sided hypothesis test with an alpha level of 100 minus C%. The relationship between confidence intervals and one-sided hypothesis tests is a little more complicated. A confidence interval with a confidence level of C% corresponds to a one-sided hypothesis test with an alpha level of half 100 minus C%. So here's what we're looking at. A 95% confidence interval for small samples. And we're going to go through a little bit of information here. When the success-failure condition fails, all is not lost. We have to be careful, but all is not lost. A simple adjustment to the calculation lets us make a confidence interval anyway. All we do is add 4 phony observations, 2 successes and 2 failures. So instead of p hat equal to y over n, we use the adjusted proportion of p equals y plus 2 over n plus 4. And we're going to get into problems at the very end of Chapter 21 that deal with this. So, A better confidence interval for proportions. Now the adjusted interval is p plus or minus z star times the square root of p minus q over n. The adjusted forms gives better performance overall and works much better for the proportions of 0 or 1. It has the additional advantage that we no longer need to check the success-failure condition, which is real nice with our writing. And I'm going to pause here when we get to this type. So this is the next thing that we're going to talk about on making errors. So I'm going to pause.